Hi folks, welcome back to Physics with Captain Rod. The purpose of this video is to introduce you to a concept called charge. All right, so I put this question up here, what is charge? And hopefully after watching this video, everyone will be able to answer that. So the idea starts here with the concept of an atom. So in this picture here, what I've got drawn is kind of a model of an atom. An atom is made up of three fundamental particles here. We've got what are called neutrons, protons, and electrons. Now, the neutrons and the protons within an atom, they reside in this central location here called the nucleus. So in this picture, these six spheres I've drawn grouped together represents the nucleus of the atom. Now you notice I drew three of them in red. What I'm doing is color coding this. So for the rest of this video, these red particles are representing protons. These gray colored or charcoal colored particles are representing neutrons. So in the nucleus of an atom, you have the protons and the neutrons. Now, you'll notice in this picture, there are three protons in the nucleus. The number of protons in the nucleus of an atom is called the atomic number. So the atomic number of the atom that I've drawn is 3. If you look this up on a periodic table, you'll see that the atom that I'm trying to model here is a lithium atom. You'll also notice that there are 3 neutrons. That matches the number of protons. And if you had a sample of lithium and you looked at a whole bunch of atoms, a lot of them will be 3 protons, 3 neutrons. But what you'll find is that some of them might have 3 protons and 4 neutrons. The number of neutrons in the nucleus of an atom, it turns out, can sometimes vary a little bit. And when you have different atoms with different number of neutrons, you have what are called isotopes. That's not important for this video. For now, we're just going to assume we've got 3 protons, 3 neutrons in our nucleus. The electrons, they live in these regions out here. So these little particles that I drew, these are the electrons. They live in this region called shells. And I tried to kind of draw the shells. This dashed line here is representing a shell. Now there's some things I need to discuss here as far as this model is concerned. First of all, let me get back to the idea of a shell. The electrons, they orbit around the nucleus. All right, they're going really, really fast. You know, these speeds are measured in thousands of meters per second. If this little electron, as it goes around the nucleus, could somehow leave paint behind it, much like one of those truck painters that paints the road as it drives down the road, and it kind of leaves that mark every here or there, eventually it would map out this region that would have a certain shape. And let me just assume, for the sake of example for the moment, that this ends up being a spherical type shape. This paint, this three-dimensional painted surface, that's what the shell is. It just represents a region where the electrons are spending their time. Now, atoms have, the lithium atom has 2 electrons in what's called its inner shell. Then it's got another shell out here where this other lone electron here would live. Now, you'll notice that I drew 3 electrons. So when you have an atomic number of 3, that does mean you have 3 protons. End of discussion. That's not allowed to vary. An atomic number of 5 means your atom has 5 protons and so forth. Number of neutrons can vary a little bit. Number of electrons can actually vary a little too, and I'll talk why in another video. But for example, here, this lone electron here, it's very easy to remove him, and you'd have what's called an ion. But your stereotypical atom has the same number of electrons as it does protons, if it is not ionized. Now, another thing I'd like to talk about before I get into the nitty-gritty here is scale. I've tried to draw the electrons quite a bit smaller than the protons and neutrons, but we have to be able to see it in the video. In reality, if the neutron were, say, the size of this actual orbit here, the electron would be just a little pinprick. I mean, the neutrons and protons are thousands of times larger. So the relative size difference between these is not that accurate. This would have to be much, much smaller, but we would have a hard time seeing it and discussing it. Another thing I'd like to talk about is the size of these shells. This shell is roughly, that distance there is a reflection of the size of the shell. Well, if the nucleus of the atom were actually this size, this first shell would be a long, long, long way away, probably hundreds of meters. There's nowhere even close to this. So this size here actually should be hundreds or perhaps thousands of times larger. Atoms are mainly just empty space. An analogy I kind of like, if the nucleus of an atom were the size of a marble and you put it on second base in the Astrodome, the shells would be out in the stands and the electrons would be the size of just a little pinprick. But All right, so I've discussed the assumptions here enough. So again, these are not, the scale is not entirely accurate. Now, let me talk about what we have going on over here on the right. These charcoal spheres are representing the neutrons. Right, the red ones, like these three, are representing protons, and then these small green ones are representing electrons. And it turns out if you get a pair of protons, or I'm sorry, not protons, neutrons close to one another, so right now, ignore everything except this pair of particles. And if you ask yourself, or I should say, you don't ask yourself, but by experiment, I'll say it's very easy to determine that there is no force of attraction or repulsion between these. None. No force. If you were to get protons and get them next to neutrons here, and when I say next to, you know, a little bit of distance away, it turns out there's no force between these either. At least not as long as you keep this distance reasonably close. Again, there is another force called the nuclear force that occurs if these get extremely close, but that's not the point of this video. All right, when we get a proton next to an electron, is there a force between them? No. However, when we take a proton and you get it close to a proton, here a force appears. In this example, the force would end up being a repulsive force. So if I drew it in the picture, that force on each of these particles would be this way. All right, so I'm just going to put a yes now. Turns out if you take an electron and get it close to an electron, they also repel one another. So I'm going to go ahead and draw force vectors in here. All right, yes, as far as is there a force between these. And when we take a proton and get it next to an electron, there also is a force between them. However, protons and electrons attract one another. So the forces would actually, in our picture, be drawn maybe like this. And again, I'm going to put yes here. So two of these particles, right, between protons, neutrons, and electrons, are exhibiting some sort of behavior, this force behavior, that's either repulsive or attractive, depending on if you're looking at proton-proton pair, or proton-electron pair, or electron-electron pair. Anytime we get these next to neutrons, so when we look at this pair, nothing happens, nothing happens, nothing happens. So the protons and electrons exhibit some sort of property that the neutrons don't, and that's what the charge is, right? So the idea of charge is it's a measurable property that we assign to the protons and the electrons because they exhibit this behavior that they repel or attract one another depending on the relative types of combinations. All right, now let me get rid of this because I don't need it for the discussion anymore. So we have this new property called charge. And it's measured by a quantity called the coulomb. And I'm not going to define a coulomb here. I will do that in a video further down the line. For now, it's enough to say we're going to measure this by a quantity called the coulomb. You could think of the coulomb as a fourth fundamental quantity. If you've studied Physics 1, you remember that mass is a fundamental quantity. Length, a fundamental quantity, time, a fundamental quantity. All of the things you studied in Physics 1, like momentum or kinetic energy, can be expressed as some multiple or some combination of these things. Well, we're just going to add another one here called charge as a fourth fundamental quantity. Now, you'll notice that there's different force directions depending on the combination. So that's taken into account with plus and minus signs. The proton is arbitrarily assigned to carry the positive charge. Now I say arbitrarily, there's a little backstory on how that came, and I'm going to save that for another video. For now, we're just going to say that, all right, the proton is positively charged. In our pictures, we would typically denote that with some little pluses. The electron is assigned to have a negative charge. I probably have trouble even getting it inside the circle. I'm just going to put it here. And if you look carefully at this picture, I had already put some pluses in for my protons, and you can't really see it. Maybe if I blow it up, if I take one of these electrons here and blow it back up here, you notice that I had put a minus sign in there to reflect its charge. So I'm going to go back and put it back to where it was. All right, so protons and electrons, they exhibit this property that they repel or attract one another depending on the relative you know, proton proton or electron electron or proton electrons, right? So they carry this property that we call charge, or probably a better way to put it is charge is the property that these things carry if they exhibit this type of behavior. And then charge is measured by what's called the coulomb. Now let's talk about the actual charges of these particles. The charge of an electron and the charge of a proton is numerically the same. Now, most books I see use the letter Q to represent charge. So the charge of a proton is positive 1.6 times 10 to the minus 19th coulombs. The charge of an electron, so I'll put a little p here for charge of the proton, and maybe an e for charge of the electron, is minus 1.6 times 10 to the minus 19th coulombs. This quantity, 1.6 times 10 to the minus 19th coulombs, this is called the fundamental unit of charge. I'm not going to write that all out. The reason it's called the fundamental unit of charge is once you get to the scale of the atom and you're talking about charged particles, this is the smallest unit that it comes in. So while I'm going over here, if we look at this atom right here, right now this atom is considered to be electrically neutral. Well, one way I could charge it is if I remove one of these electrons. Now I should probably point out why it's neutral here first, because it has 3 positive charges. So the charge in the nucleus is positive 1.6 times 10 to the minus 19th coulombs, but it has 3 electrons, each of which carries a charge of negative 1.6 times 10 to the minus 19th coulombs, and if you add all those numbers up, you get 0. Now I can charge the atom, and I can do so by removing an electron. So maybe I take this electron and we take it over here somewhere. Now, if we go back to our atom here, it now has 3 positive charges and only 2 negative charges. So the atom now has a charge of positive 1.6 times 10 to the minus 19th coulombs. If I wanted to charge it further, well, one way I could do that, remove another electron. And again, don't worry about where they're going, but just suffice to say the atom doesn't have them anymore. And now the charge of this atom would be 2 times 1.6 times 10 to the minus 19th coulombs. So if you carry that logic further, what you'll realize is the charge on this atom, whatever it is, I'm going to say big Q, it has to be some integer multiple, I'm going to put n here for an integer, times the fundamental unit of charge, 1.6 times 10 to the minus 19th coulombs. And this is true for all charges once we're talking about the scale of the atom or larger. All right, so I think that's enough for this video. I see I've hit 13 minutes here. I'd like to keep these under 12 if possible. So again, let me kind of recap here. What is charge? It is a property that we assign to the protons and the electrons because they exhibit this behavior that they repel or attract one another according to their relative signs. Now, the proton is assigned to have the positive charge, the electron the negative charge, and the reason we need a negative number here is that as you get further in physics, you'll find that whatever a proton does in any given set of circumstances electrically, an electron always does exactly the opposite. The forces are always in the opposite direction, and that's what the minus sign is used to take into account. So the proton carries this charge, the electron carries this charge, and we say that the charge on a neutron is 0, and actually its name is actually derived from this concept. So I hope this video helps demonstrate what charge is. Have a great day.